Hello everyone and welcome to another episode of the Quantum Hidden Champions. In today's video we are going to talk about a company that starts with our favorite Greek letter when it comes to quantum. Let me know down in the comments below what is your favorite Greek letter when it comes to quantum. But I think the one that I'm always thinking about is Psi. If you don't know these Greek letters, you're also completely fine. We are not going to dive into any quantum physics formulas today. We are going to try to understand what PsiQuantum is actually doing. Reading the first sentence in Latin letters here, building the world's first useful quantum computers. And then we see some wafers, some wafer processing here in the background, some vacuum machines, people in clean room suits. So just looking from this, I think it has to do something with, let's say, CMOS type of processing, so clean room processes, but also, there's some metal stuff happening here. Introducing Omega, a manufacturable chipset for photonic quantum computing. So with that, we already know this company is working in the photonic space, so they're using light to do quantum computing. Moving on, first principles. PsiQuantum is a quantum computing company on a mission to build and deploy the world's first useful quantum computers. Our approach to building a utility-scale, fault-tolerant quantum computer involves photonics-based architecture, and it leverages existing infrastructure to build and scale these systems as fast as possible. The approach: research, blueprint, applications. So research for PsiQuantum's team of quantum architects, chemists, developers, engineers, and theorists. Blueprint, a path to large-scale fault-tolerant quantum computers based on photonics approach. And then applications, developing use case for the first useful quantum computers capable of solving intractable problems. There's also a news section down here. I'm recording this beginning of September. There doesn't seem to be many new things added, at least on the starting page since then here. Let's quickly check out the About page. PsiQuantum has one mission: to build and deploy the first useful quantum computers. In 2016, PsiQuantum founders uncovered a viable path to building large-scale fault-tolerant systems by taking a photonics approach and leveraging the advanced semiconductor manufacturing industry and other existing industries. Nearly 9 years later, so 16 plus 9 is 2025, which is now, PsiQuantum is building thousands of wafers for quantum chips, testing production cryogenic cabinets, and developing fault-tolerant algorithms to deploy on our first systems. Our work continues. Then we see here the executive team of people bringing together 60 years of foundational work with decades of operational experience. Our approach is enriched by diverse backgrounds spanning academia to Fortune 100 companies. So you see the different people here. There's government advisory board as well. And then you see there's partnerships down here. For example, with DARPA in the US, Australian government, Queensland government, Los Alamos National Laboratory, but you also see the investors here like BlackRock, Playground, Redpoint. So there's very well-renowned investors as well. And then, there's also a career tab here. Let's quickly check the blueprint part of it. A fast path to useful error-corrected quantum computing based on photonics, single particles of light, leveraging existing semiconductor manufacturing, packaging, and high-power cryogenics cooling technology. So current systems, then we see here a lot of noise on the signal, can beat the world's fastest supercomputers in artificial benchmarks, often require extreme and exotic cryogenic cooling, and are too error-prone to solve commercial valuable problems. Now, useful quantum computers must be fault-tolerant and fully error-corrected, capable of running known, classical, intractable, useful algorithms, and will require advances in architecture, networking, modularity, and control electronics. So then I guess here now we see the different stages. So the first one is the wafer. The wafer is usually a silicon disk, like a crystal, where you put the different layers of materials on top that then become a chip. So you can see here there's this pattern which is being repeated throughout this whole disk, right? This is usually like a single chip, and then you kind of cut it or dice it into these single devices, and then you actually end up with the single chips. So here it says wafers tested more than 1K, so more than 1,000, and then devices tested is more than 1,000,000, because usually on such a wafer you have a lot of these devices. And that's exactly the same stuff that also goes into your smartphone, into your computer, into your tablet, whatever, even into your washing machine. It's all made on these wafers here with these high-tech labs, which we see here on the left side in this video. So this is now at Global Foundries. There are other ones which are also producing these wafers. I think TSMC is a lot in the media recently, but also, for example, Samsung has their own labs, their own fabs where they produce it. Intel has fabs, so there's like different of these silicon fabs. Now onto the chip. So it says photonic qubits are implemented by reposing integrated photonics technology, originally developed for telecom and data center networking applications. Again, as you might know, we use fiber today for like high bandwidth communication tasks. So for example, when you connect a data center with another data center, you sometimes have a dedicated fiber line between those. And then light is actually being used to transmit information through these fibers, which basically means that you have some photodiodes, some integrated electronics. And you see that also here you have these fibers, which I guess are like telecommunication standard fibers. And then you have this high performance optical switch on there, photon source, single photon detectors, which as far as I understand, all relies on these standard technologies, and then is of course changed so that it can work in the quantum regime. Here it says entangled states, specially designed to implement quantum error correction codes, are created and measured using fusion gates. Non-deterministic photon sources and gate operations are made scalable via combinatorial multiplexing and loss-tolerant error-correcting codes. Then you see here a fidelity of 99.99% for a single qubit and a 2-qubit fidelity of more than 99%. Fidelity is basically a benchmark or a number that tells you how accurate a system can perform a specific quantum gate. Then comes the packaging. Packaging, for example, if you think of, let's say, your smartphone, you start with the silicon wafer, right? That's what comes from, I don't know, for example, here in this case, Global Foundry, you have the wafer, they cut it into dice, and then you have like the smaller pieces of the wafer, but now you need to somehow electrically connect them, and this is not what goes right away into your smartphone. So there will be a plastic housing around it, so it has to be packaged in a way. That includes things like bonding, that includes things like molding, that includes like things like, I don't know, physically gluing something on a chip carrier. It can be very different types of processes, but at the end you end up with like the finished component, and that's also what you see here, right? So you have heat sinks, control chips, photonic chip, circuit board, and the optical fibers, and that all goes into this big or let's say bigger system here, which is a sample of an advanced cryogenic package. Okay, so it says photonic chips are integrated with cryogenic control electronics into a manufacturable package. Despite the fact that some of these packages must be operated at cryogenic temperature, we are able to predominantly use conventional technologies, PCBs, so printed circuit boards, copper heat sinks, and bump bonding. So bonding as in like connecting the chip to some standard interface, because if you, for example, have the silicon chip, you somehow need to figure out a way that you can connect the cable or you can connect the printed circuit board to it. And usually for that you have this chip carrier, for example, and then you have this needs to be somehow bonded to the PCB, and the connection between the between the chip itself and the chip carrier is, for example, done via this bonding process. But there are different ways. You can have like little wires which are connecting the chip to the chip carrier, and there's also this other technologies like bump bonding. As a result, PsiQuantum can leverage conventional contract manufacturing to build large numbers of packages quickly. Photonic qubits can be networked and modularized using standard optical fiber without transduction, a huge advantage at scale. Then there's the cabinet, which this whole thing gets integrated into. Here it's so that includes then, I guess, the cryostat, like the cryogenic equipment. Why do you actually need a cryostat? That's because operating at room temperature, everything is for quantum systems hot. And heat basically means there's like statistically distributed energy within your system. So like atoms are shaking and wobbling, and they are not wobbling all at the same rate, but like this is the statistic process. So it's a very uncontrolled systems. And in order to be able to measure these quantum effects where you can really separate, for example, single atoms from their whole environment, you actually need to cool down everything. And usually it's not enough to cool it down to like 7 degrees Celsius, but you have to go really, really low to the absolute zero. Absolute zero is minus 273.15 Celsius, I think. So then you usually use the Kelvin scale. Kelvin starts with 0 at absolute zero. If you use liquid helium, you come to about 4 Kelvin. If you use what is called a dilution refrigeration cryostat, which uses the normal helium, which is helium-4, and an isotope of helium, which is helium-3, and you kind of you dilute them and then you split them again. With that, you can reach even lower temperatures, such as 10 millikelvin using this dilution technology. And here you can see it's liquid helium delivery, optical feed-through, and heat-shielded system. So I guess this is also going down to very low temperatures. But let's see. Photonic qubits do not feel heat, do not decohere, and can be operated at high fidelity at room temperature, while the superconducting detectors needed to high efficient readout for photonic qubits do require cryogenic cooling. They operate at 4 Kelvin relative to 10 millikelvin for superconducting qubits. So basically what needs these low temperatures here is the readout part. So you use the photons to generate some or to process some quantum information. You operate some gates on them, but then like if you, for example, put a photon into superposition and now you want to actually read out, is the photon here or is the photon here? Then you need a detector which is able to detect a single photon. And these detectors, they actually need to be cooled down because, again, like if you have a room temperature readout system, like a room temperature detector, you have so much thermal noise, like basically thermal noise, that you cannot really differentiate between noise and the single photon reaching the detector. One example of how you could, let's say, easily build such a detector system is if you had a superconducting strip, so like a piece of metal that is superconducting. And usually these superconductors, they have a critical current. So if you ramp up, let's say, the current to 10 milliamps, it stays superconducting. But if you go another milliamp up, like to 11 milliamps, then it becomes normal conducting. And this curve is a function of temperature. So if you are at 4 Kelvin, it might be 10 milliamps. But if you go up in temperature to 5 Kelvin, it might only be 9 milliamps. So now you take this stripe, you apply these 10 milliamps through, like the current. Now if a single photon hits the metal, it actually locally heats up the superconductor a little bit because it gets absorbed. And this heat up might already be enough to actually collapse the whole superconducting state. and suddenly, your superconductor becomes normal conductive, so it switches the phase. And that's something that you can easily measure and resolve. So that's an example of like a cryogenic single photon detector. And of course, there are other ways to implement that as well. PsiQuantum is building and testing cryogenic cabinets with thousands of times more cooling power than the largest dilution refrigerators ever built or operated. Because of the higher operation temperature of photonic qubits, these cryostats can also be surprisingly simple and can be built using existing cryogenic technology. So you can go up to 100 watts of cooling power, which is much more than these dilution refrigerators have. And that also means you can build them in a much bigger scale, because usually, and that's also where like a lot of this quantum technology is right now limited in a way. If you have, let's say, a small chip and you put more qubits on there, that also means you need to add more of these control lines, right? You need to feed more signals in there, and every single cable that you draw down to the chip, this cable is also again a heat connector, because you cannot perfectly insulate that. It will always carry some heat down to the chip, and because of the fact that the cooling power of these dilution refrigerators is very limited, there's a limit at which like how many qubits you can actually put on a chip. So at some point you have to start like connecting multiple of these cryostats and these chips somehow with each other, which becomes a whole new scaling problem that will at some point occur. And there are like ways to push this out a little bit. You can, for example, put your control electronics to cryogenic temperature. That way you don't have to draw that many lines all the way down, and that way also the temperature drop will not be as strong as like if your whole control stuff is sitting at room temperature. So you can do some, let's say, intermediate processing on a cold stage somewhere in between, and this is something that people are developing in the superconducting space. But yeah, right now this 4 Kelvin technology is much easier. This is, I think, for example, something that is being used in these big scanners that you have in the hospital, like MRI scanners, the tubes that sometimes people are being put in for scanning. I think these operate also on this 4K technology, so it's something that is actually already proven and being used. Okay, then it says compute site here. So you have the cryo plant, you have the compute building, you have the office. It says most architectures for quantum computing will require a data center-like facility in order to deliver enough qubits for commercial useful applications. PsiQuantum is partnered with both Daresbury SFTC in the UK and the SLAC National Accelerator Laboratory in California to validate intermediate scale systems for network cabinets. In 2024, PsiQuantum announced 2 landmark partnerships with the Australian federal and the Queensland state governments, as well as the state of Illinois and the city of Chicago, to build its first utility-scale quantum computers in Brisbane and Chicago. Recognizing quantum as a sovereign capability, these partnerships underscore the urgency and race towards building million-qubit systems. In 2025, PsiQuantum will break ground on a quantum compute centers at both sites, where the first utility-scale million-qubit systems will be deployed. And that's what it basically looks like. So you have the cryo plant liquefying the helium, so that it can be used for these detectors here. You have the compute building with all of the compute units in it. And then, okay, there's an office here as well. Then there's also the software side of things. Our software enables programming quantum computers using a familiar language, which is Python. It affords programmers the ability to specify algorithms at high level using contemporary primitives such as quantum signal processing, quantization, and block encoding, and automates the compilation of individual gate operations. We have a growing library of over 50 proven quantum algorithms and subroutines that are callable by any application, reducing development time and improving the quality of domain-specific applications. while we have a very fast qubit simulator, our main emphasis is on optimizing of resources requirements for fault-tolerant implementation for quantum algorithms. We are working with partners from industry, academia, and government to develop and optimize quantum algorithms for a broad range of valuable applications, which is more than and it says more than 50x reduction in gate count. And here, we see the PsiQuantum workbench and QRE SDK. Okay, I think this actually is a very interesting page, the whole blueprint concept, because, and that's like at the very core of, I think, what PsiQuantum's message is. They actually want to use existing infrastructure, existing technology, and use as much of the stuff that is already existent and like scalable and easy to use in order to push this quantum move. So like they use fiber technology, they use existing programming languages, existing cryo technologies, existing fibers, existing CMOS. So it's like all the stuff that is already there, which all of them, of course, has a little notch towards quantum, because you have to use these single photon detectors, which is maybe not the most standard thing. You have to tweak maybe Python a little bit that you can actually do quantum programming with it. So there are like certain things where like it will get a quantum notch towards it, but it is really like facing towards like we don't want to do all of the exotic stuff. We use the stuff that is out there, that is existing for like larger scale applications, and then try to integrate all of this into quantum, which I think is a very unique approach that I haven't seen to tell the story that specific way. I think is something that I haven't seen with many of the companies, because I mean, if you're looking into a quantum computer, there is a lot of technical complexity, and a lot of people like to talk about their unique approach. But here the storytelling, I think, is more like we try to do as less unique stuff as possible, use the stuff that is out there, and then make something new with it that will actually reliably work and be scalable. And I think the be scalable part is also very important here. There's also something here about the research they are doing. So there's like publications here that have been going out throughout the years. There's also a careers page, and there's the news page, which we have seen already before. And I think with that, we are already at the end of PsiQuantum. I hope you liked it. If so, please make sure to subscribe to this channel to not miss out on the next video. Until then, see you soon. Bye bye.